One of the videos for today talked about average rates of change and how we calculate average rates of change, average velocity. I think it pretty much focused on that particular rate of change, but rates of change can be represented in a lot of different ways. Velocity is definitely one of those, but let's take a look at another type of problem, and we'll kind of work through this and see how we can at least approximate a rate of change, an instantaneous rate of change. We may not be able to find the exact value of it, but we can at least get pretty close. Here's an example of the path a bicyclist is taking, and they show the graph of it. We see the function that represents that, I guess, kind of a hill. That's my kind of hill where it's not too steep. I may be able to bike up that one, maybe not. But the problem, bicyclist riding along this path modeled by the function f of x equals 0.04 times the quantity 8x minus x squared. X and f of x are both measured in miles. So find the rate of change of elevation at x equals 2. Rate of change of elevation. Well, it's not the rate of change of velocity, but it's going to be calculated very similar to what we would with rate of change of velocity. Rate of change of elevation at x equals 2. What's another way to think of that as we're looking at this graph? Okay. Rate of change is much like thinking of the slope of a line. And in fact, technically the rate of change, not the average rate of change, but the rate of change exactly at x equals 2, that's going to be the, almost got it, that's going to be represented by the tangent line. And the slope of that tangent line will be the rate of change of elevation at x equals 2. Now the problem is, how do we find the slope of a line? Well, yeah. In algebra, how do we find the slope of a line? We need 2 points. But in this case, we only have 1 point. Now, in calculus, we'll figure out what we can do to find that. And like Tim said, we'll be taking the derivative to be able to help us with the slope of the tangent line. But to lead up to what the derivative is, we've got to look at this in terms of the slope of a line through 2 points. Okay. On this graph, we're only looking at 1 point, which the y value when x is 2 turns out to be what? Okay, now you may need your calculator to, I can't quite do this one in my head, but so we get a function value or a y value of 0.48. So we have our point, x equals 2, y equals 0.48. Now, using the function, using f of x here, how would we be able to approximate the slope of that tangent line? Now we're, again, not able to find the exact value of it, but we can come pretty close. What would we need to do in order to at least get an idea what that slope is? What did we say we needed to find the slope of a line? Okay, we need 2 points. We've got one, but we need a second point. And where should that second point be to give us a pretty good approximation for the slope of the tangent line? Well, we need to find a point fairly close to x equals 2, and the closer the better. So let's pick out a point here at maybe 1.9 and calculate f of 1.9. That one I definitely need a calculator to do that. Somebody have that? Okay, so 0.4636. I didn't leave enough room, but was that the exact? Okay. In this case, we'll go ahead and keep all the decimal places as we calculate or approximate the slope of the tangent line. We'll probably need as many decimal places as we get. So the slope of the line through the point 1.9, 0.4636, and the point 2, 0.48, well, change in y divided by the change in x. Slope of that line would be what? So 0.164 for the slope of that line. Now, let's take a look at what this would mean. I'm going to go to the next page and redraw this, where we're going to draw about this much of the picture instead of the whole thing, and we'll blow it up quite a bit. Now you just have to use your imagination when I start drawing what it should look like, not necessarily what I draw it like. But that curve might look about like that, and then the line that we're calculating would be like that. So 1.9, 0.4636, and 2 and 0.48. So the rate of change, well, we're going to get a pretty good approximation to that slope of the tangent line by using these 2 points. What did we come up with? 0.164? Is that right? Okay. How would we get an even better approximation to that slope of the tangent line? Looking for the slope of the tangent line here, what could we do to get a better approximation than what this is? We need to get closer yet than even the 1.9 that we chose the first time. So we could go 1.99. Okay. or 1.999 or 99999, how many ever nines you want. Let's do the 1.99. See what that gives us. Function value, that was the 0.04, and then times the quantity 8x minus x squared. What do we get with 1.99? I bet it's going to be pretty close to that, but a little bit under that one. So f of 1.9, 0.478396. And now let's go ahead and calculate the slope between this point and this point, which on the graph would probably be somewhere in this neighborhood, which there comes a point where it's just too small to see any difference, but numerically we can calculate the slope, change in the y value divided by the change in the x value. And what do we get for that? So 0.1604 this time. And as you do this over and over again, you start to notice a pattern. At this point, I'm not sure I would say there is a pattern, but we do one more calculation with 1.999, and if that pattern holds true, I think let's go ahead and do one more here. F of 1.999. Go ahead and calculate that, and then we'll calculate our slope. I bet I'm correct up to 2 decimals here. So with that y value, we can then go with our 2 and 0.48, and this point here, calculate the slope. Let's see, that's not a 0. 2 minus 1.999. And what do we get for a slope there? So at 1.9, when x was 1.9, we had a slope of 0.164. At 1.99, we had a slope of 0.1604, and now with our x 1.999, we get 0.16004. Well, as we kind of figure out what's happening here, we can get closer and closer and closer. Just continue to make our x value 1 point and then hundreds of nines. Well, technically that's still a different x value than x equals 2, but we are getting closer and closer and closer. And what we're really ending up with is the denominator gets very, very, very close to 0. Like we said in our previous discussion, we cannot divide by 0, but we can divide by a very small number, as long as it's not exactly equal to 0. So as we kind of generalize what's happening here, what do you think the slope of the tangent line is going to be? looks like it will be exactly equal to 0.16. Now we can't guarantee that, we can't prove that right now. A few weeks we'll be able to prove that. But the idea is it sure looks like we're getting closer and closer and closer to this value. By getting closer to 2 with our second point, we're getting closer and closer to this value right here. So now all of this discussion was in terms of slope of a tangent line, but really what we were looking for is the rate of change of elevation, okay, as this bicyclist rode up a little bit of a hill. Well, what does this 0.16 represent when we put it in terms of rate of change of elevation? What we've done pretty confidently said, well, slope of the tangent line would be 0.16, but how does that relate to rate of change of elevation? What we need to think about, slope is calculated as change of y over change in x, or really any rate of change of y over change of x. Well, what was the y value representing in this problem? It's going to be the elevation. How high is the hill that this bicyclist is riding over? So change in elevation well, our 0.16 is a decimal, not really a fraction, but we can say 0.16 over 1. What we're going to be able to describe here at x equals 2, which would be 2 miles from wherever the origin was set in this picture of this hill, 2 miles horizontally from that origin, the elevation was, the y value was 0.48, but the change in elevation is this 0.16. So what this represents is we're going up 0.16 of a mile for each 1 mile horizontally. And that is specifically when x equals 2. That changes as we continue to ride our bike up that hill, but at that very instant, we've estimated that the bicyclist is going up at a rate of about 0.16 miles for every 1 mile horizontally. Okay, and of course we'll get deeper and deeper into this idea as we go and start talking about derivatives, but we've got a lot of groundwork to establish before we jump into the derivative.